That's fine.
Who's that?
That's one of the, he's like super famous for his lectures in the 60s. Richard Feynman.
Oh, fine. Oh, yeah. The physicist, yeah. That does have to be, right?
Yes.
Hey, good morning, everyone. So just a reminder, today is the last day to opt out from the final exam. So if you don't opt out and you don't take the final exam, your grade final exam will be 0. Yes. Yes. No. I don't have, I don't have final exam. I don't have the project. I don't have any stuff. So, and then we have homework 7 due the 21st, the project due 21st, and the final exam 28th. Any question? Yes, sir. No. Today is the time to choose. Okay, it's more fun this way. So, okay. Okay, I'm really pleased to have Ryan Pinkert here to give us the lecture about active learning. I think it's a very exciting topic. This is not a new topic, but at the same time, there is quite a bit of a new life into this topic in the last couple of years. And this is what really Ryan does for his PhD thesis work. So he will share the basics and then what to look for. And I think Mia, she's not here. She asked about like retention and then switch events. So he will touch base on those at the very end of the lecture today to some extent, right? Okay, it's all yours.
So, hi everyone. I'm super excited to do this lecture today because it's probably one of the hottest topics that's around in deep learning right now. And well, if you think about what has been done so far, right, or what you guys have talked about so far, you've typically talked about areas where the data that you've been looking at in deep learning algorithms has been fixed, right? So you've always had a fixed number of training samples, you've always had a fixed number of testing samples, you always had a fixed number of labels available to you. Now, what I kind of want to shift away from this notion in this actual lecture today, and I actually want to talk about what happens if we don't have enough labels. And what I mean with this is that in typical industrial scenarios, right, you don't have, you only have a limited amount of money, right? You only have a limited amount of resources to actually label data, right? So imagine you have like an autonomous driving company, right? And you would like to get a bunch of samples for object detection, right? If you want to essentially decide or at least find the specific, or you have a ton of driving data available to you, which data do you send to a labeling company to essentially get the maximum amount of feedback from your machine learning model? And I kind of want to illustrate this with a toy example over here, right? So imagine you have this humongous amount of unlabeled data. So imagine you've driven around with your car and taken a bunch of videos from a bunch of different locations, a bunch of different pedestrians, a bunch of different cars, and you would like to train a system that can do autonomous driving on this, right? Now, which part of the video do you send to the labeling company and label, right? And I'm going to illustrate this with this toy example. So if we move away from this complex scenario of self-driving cars and simply go to classification, which you all are probably well aware of, let's imagine you have this data set where you're trying to classify these 3 different things, right? So we have a fish, we have a toad, and we have a frog over here. And we have the following labeling constraints, right? So we have a humongous amount of data, and we want to decide which one of these are we going to send to the labeling company to derive a training set to label. Now, the cost per labeled sample is going to be $3, right? And the total amount that we have available or the total amount of money that we have are $9. So I mean, that's very simple math, right? At the end of the day, we can label 3 samples. So looking at these different classes, right? Which samples do we send to the labeling company to essentially annotate, right? And well, you could first off just randomly select some, and you might actually get something that looks like this, right? So this is the first selection. We select these 3 samples and we label them, and that consists our training set for our model. So of course, just looking at this may not be the best idea. So you may actually do a different selection, which is the one at the bottom over here, right? So you select these samples at the bottom, right? And then the third possibility is going to be this one, right? So just intuitively speaking, which one of these three different selections, if labeled and if this is our training set, right? Which one would be the best one, right? Yeah. Yeah, of course, right? So that's because, but the reason why you know this, just intuitively speaking, right, is because you know that this one here's a toad, this one's here's a fish, and this is a frog. But in real life, you won't really know this. You can imagine all of these just bunched together in one single blob, and essentially imagining which ones of these would you select to label and add to your training set. And that's really at the core of what active learning is. The question of deciding which ones of these are you going to be sending to the labeling company to essentially annotate, right? And which you're going to be using for your training set. So that's going to be the center of today's lecture, meaning which selection of these samples are we going to go for in order to maximize the performance of our active learning of our algorithm, of our deep learning algorithm, if we only have a limited amount of budget available. So that was basically discussing about why we're doing this, right? I'm going to be going through the fundamentals of active learning. I'm going to be talking about how we can incorporate the model and let the model actually decide which ones of these unlabeled samples we're going to be using for our training set. After that, I'll be talking about three different major blocks that really consist of what active learning actually is. It's going to be talking about how do we select these samples on a difficulty-based approach, a diversity-based approach, and a fusion-based approach. And I'll be finishing off with some open research problems, which is a really exciting topic. And that's where I really want to go to from here. So before I go into it, did everyone here understand what the premise of this problem is and why we're actually interested in it? Are there any questions about this? This is actually very central. Yes.
So they have a big number of classes like we had in the last slide. The two they use are similar. So for example, the frog and the toad.
Yeah.
If you send 4 images of the frog or the toad and then one of the fish, could you not then get a better understanding of what 2 of them are and then what one of them isn't? Can you use that as a classification?
So you're essentially saying if we have two of the fish or 2 of the toad?
Then you get more data on like how one looks, and then the fish is just so different that if one is the toad, but it's similar to the toad, but it's not the toad, then it would be the frog.
So that is a different. So what you're talking about is actually zero-shot learning. That's another area of research. So if you think about for instance, that you want to learn what a zebra is, you could learn what a horse is, and you could learn what black and white stripes are, and you could combine these two. So yeah, of course, you could incorporate that into your active learning algorithm, which could give you a leg up on it. Or, the actual way you could also just select is if you go for these 3 in the first place, right? So both of these are valid. Yes.
These are candidates to be left. Doesn't be have head of profession. Now you have to figure out what you're listening. It might be a criteria, but that will something that actually in edit. You have to give it a bunch of images, but 10 of them that are candidates to be left. Now, which one of those you will send the data to? The fewer the better, right? So now, take your scenario. That's actually against what I just you are sending 5 of them, but actually this budget
yeah.
How far away are we from each other?
Well, that's a very open-ended question. Yeah, that is very much true. Sorry? Depends once again what you define as what's human intelligence, right? Do we define human intelligence as the way we perceive the world, for instance? So how accurately am I able to position everyone around me? How do I know how far you are away from me, right? Or are we talking about, solving machine learning paradigms, doing open-ended research, right? So all of these are different ways you could define human intelligence as. So let me direct the question back at you. What do you mean with human intelligence? Oh, okay. Well, I mean, I feel like that could be you can ask me that after the lecture, then we can have a very long discussion about it. But I feel like that kind of goes beyond what I want to kind of address today. Okay, so now that we have the actual motivation behind all of this kind of figured out, let's kind of go into the fundamentals. And what I actually want to talk about today is how we can incorporate a deep learning algorithm into the selection process, right? So you remember, we want to select the data we want to send to the labeling company, right? And this labeling company essentially defines what our machine learning model actually is. So a very intuitive way of doing this, right, is let the machine learning model essentially help us in selecting the data points that we want to send to the labeling company to essentially get the best possible algorithm we have, right? So in other words, we want to leverage the information extracted from the model. So imagine we have this 3 data set points that I just described over here, right? The idea is that we want to input it into our machine learning model, into our deep learning model, right? And then essentially select these, have the models say we want to select these 3 data points to essentially send to the labeling company. Remember, as Hassan said earlier on, we do not have any knowledge that these 3 classes are essentially separate. You can imagine it as one massive data folder, right? Where a bunch of pictures where you have no idea what anything is, right? So essentially the idea is you send your machine learning model on it and tell it and let it tell you which ones you want to send to the labeling company. And in order to do this, I kind of want to bring this entire workflow in a very high level sense before we actually dive into the math behind it. And the idea is that you first let the model select the data points, and then once you have these 3 data points selected, right, you take the human in it, which essentially labels it, which in our example is the labeling company, right? And that gives you these different colors and actually gives you an idea of what the different labels are that you can train your machine learning model on, right? So is this clear that we need is this general workflow clear before I dive into the math? Yes.
Well, paradoxical. You add an ML model, then the first step number 1 is take unlabeled data and set it to a model.
Yeah.
I thought the goal of this was to develop labeled with make model.
Well, you're essentially right. At the very beginning, we are assuming that we have an initial small amount of labeled data, which gives us this machine learning model, which I'll go into in detail in a moment. So essentially, or you can think about it in a transfer learning setting. If you don't have anything, right, you could train this thing on other data that's out there, right, that's already available in the internet, right? Then you could take the data set that you're interested in, and then you could plug it through, and that gives you this whole entire workflow. You see. Exactly. Yes.
Yeah, I guess I'm trying to figure out where the weights and biases from that model came from. It sounds like it was existing.
Exactly. Trained previously. Correct. Okay. Now let's kind of bring a bit of math into this. So now I'm going to go a bit more into detail of how this workflow looks like. So remember the workflow that I just showed, this is the exact same thing. This is just a bit more formulated out. So you have this big, humongous amount of unlabeled data. This is the machine learning model we were talking about. And well, now I want to kind of open up this big black box where we previously had select data points, right? So we start with this unlabeled data pool that you see over here. We push it through our model, right, which is FW of X with the weights W, and where X is basically this unlabeled pool, right? And as you already mentioned, this thing is already trained beforehand on this labeled training subset, which we have, right? Then that gives us this representation space of these particular samples. So think about it as the output vector of this thing, right, is going to be a representation, or is going to give you a vector of features, which are these particular representations that you see over here. Now, these you want to essentially rank and basically say, among these features, right, which ones are the most informative for this particular machine learning model, which we define with this acquisition function, right? And this entire piece that's in here is essentially doing that informativeness ranking that I was just discussing, right? So imagine you have this function, which is called A. This is the acquisition function. You can plug in any specific feature over here, right? And that'll give you a value for this particular feature, right? Which is going to be defined as the informativeness. And then the idea is that you're going to take the samples from these features, right, that maximize the informativeness of this function A, right? So you plug in the feature, which gives you a simple number, and then you take the samples which have the highest number, the highest informativeness score, right? Now, these ones you select, you send to the human to annotate. This I'm denoting with these coloring, right? So now we don't have a unlabeled feature space anymore. We have a labeled feature space, and then we add them to the training set, right, to our training subset that we just discussed, right? And then you can essentially retrain the model on this new, bigger training subset. So once again, very, very important piece. So if I lose you guys here, the rest is going to be very not fun, okay? So is this part clear? Yes. Mhm. So now you're talking about the way all of these systems are implemented in an industrial setting. But what you're essentially going at is a bit of a different setting, right? So you're basically saying you're giving it the feedback and it's collecting data about you, and that you're essentially labeling the data that you just gave it. Now, that is an acquisition process, I'm sure, probably Google or Facebook or all of these things actually do. But it's also very much also related to this framework, right? So this essentially, you're essentially giving it the labels that are already available. But this framework is actually targeted at if you have a humongous amount of unlabeled samples, right? So imagine you're Google and Facebook, right? And you collect a humongous amount of images, you collect a humongous amount of text inputs, right? Which ones of these do you send to the labeling company, right? Yours, you don't have to send to the labeling company anymore. You just got them on the side, right? Because you already provided the annotations, right? Yes. So the model is producing these are the FW values, right? So you can imagine you're pushing a picture through a function that gives you a vector. That vector are those features. So imagine that vector of features. This vector of features you're going to plug into this acquisition function that gives you an informativeness score. So how important is it? Exactly. We haven't really talked about how exactly these acquisition functions essentially substantiate into actual implementation. I'll go into detail on that in a moment, but that's the general workflow. Okay, great. Yes.
The goal here is to find the data points that best capture the essence of that flag. Right? It's the most triangle-y triangle on there.
So that is, you'll see in a moment that there are different strategies that you can essentially say which ones are the most informative. You've just given a definition of informativeness, right? That is one possible way you can define informativeness, but you can see in a moment that there's a lot of different ways we can do it. Okay. Now that the general workflow is clear, I kind of want to talk about how we evaluate these particular algorithms, right? At the center of all of this is this acquisition function A, right? So how well did we define informativeness? How well is my model able to approximate this informativeness, right? That's really what defines the quality of our active learning algorithm. And the way we can really look at it is if you have a number of annotated samples on the x-axis, right? So the size of our current training set, if you think of that loop, right? The larger this essential training subset is, so the more labels we are able to send to the labeling company, right? How good is our resulting algorithm on the test set? So imagine you just send a bunch of samples to the labeling company. That gives you a new training set. You can train the neural network on this training set and essentially log the performance on the test set. Now, as you increase that training set with this algorithm, right, with this acquisition function, how well does it perform on the test set? That essentially gives you this curve. And the higher this curve is, the better your active learning algorithm at the end of the day actually is. Because it means that you're able to, the samples that you selected for labeling and that you train your network on, the better your network is on the test set. That is really what we want to evaluate on. So that kind of brings me to the first set of major active learning acquisition functions. So we just now talked about what active learning actually is. We talked about the actual workflow. And now I want to talk about how we can fill out these different blocks, this acquisition function, this notion of what informativeness actually is. And there are several different ways you can do it. And I'm going to be presenting 3 of the most common ones. And the first one here is this difficulty-based active learning approach. So the whole idea behind this is that we define the most informative samples as the most difficult ones for the model to generalize to, right? So if you have a model and you have this frog and fish example that I just gave you, if you have a there's actually a toad that's called false toad, for instance. It looks very much like a frog, okay? So if you have one of those, that would be a very difficult sample, for instance, because it's hard to distinguish from the frog. And if you think about it from this representation space, right? So if you have this model and you push, once again, all these images through and you have all these features, these really difficult samples are going to be, for instance, outliers. So ones that are pretty far away, that are really close to the decision boundary at the center, right? So all of these samples are going to be very difficult. And those are the ones we really want to select, right? And those are the ones that these difficulty-based approaches want to select. And there are essentially 3 algorithms that I'm going to be presenting today. One of them is going to be centered around entropy. The other one's going to be centered around least confidence, and the third one around margin. So before I go into that, everyone clear on difficulty? Cool. Great. So let's start with the first one, entropy. So if you remember deep learning algorithms, right, and you look at the output of a deep learning algorithm, it's actually a distribution, right? You get a probability of something. If you remember the 3-class problem, you'll get a vector of 3 at the end as an output of your model, right? And each of those, if you push them through a softmax function, will give you a probability score from 0 to 1 for each of those different vector values. So the probability of it being a toad, the probability of it being a frog, and the probability of it being a fish, right? Now, and if you guys had in some information theoretic classes before, you've already probably heard of the information content of a particular distribution, right? So if you have a distribution, you can measure its information content with something we call entropy, right? Entropy, without going too much into details, is the probability times the logarithm of the probability, right? That will really, and summed up across the vector. That will really give you the information content of this probability distribution. And a very intuitive way of thinking of this entropy score, right, of this entropy evaluation scheme, is to take the resulting probability, right, distribution that is has the highest information content at the end, right? And we want to select all the samples that result in the probability distribution with the highest information content. And if you think about the acquisition function here, right, that essentially means nothing other than summing up all of these probability or all of these entropy scores, right, for all of these particular samples, right, that you want to select for labeling. And the sum of all of this entropy, right, should have the highest score. That's really what you can see over here. And if you think about it, in terms of where in the representation space are you going to be selecting particular samples, I kind of want to direct your attention to this thing here on the left, which is exactly the output of our softmax distribution, right? You can imagine all of these different pieces here being different classes, right? And if you walk around in between over here, that essentially gives you the probability scores for all of these different classes for one element of the vector, right? And you can see that the highest entropy values, which are these orange or red ones, are really centered around the middle here, which is kind of what you want, right? Because if you think about the decision boundaries also being over here, that's going to be some very, very difficult samples at the center of your probability distribution that you're really interested in. Okay, there was a question over here. Are you okay? So that kind of concludes what entropy is. Now, least confidence is actually very similar to this concept. And that's the most intuitive, or it's a very intuitive one, which is essentially saying, let's just take the sample that we're the least confident in. So if you think about the output of our neural network again, that means if we have our distribution and we take the highest value of that distribution, right? So if the model classifies frog, fish, or toad, it comes with a certain probability score. We simply take the samples that have the lowest probability score, right? Which we're the least sure about. So if you think about this thing, right, once again, the acquisition function essentially means you're maximizing, you're taking the highest probability score of your output distribution, and you're essentially taking all the samples which have the lowest probability score, where we're the least confident in. Now, if we bring this all back to this image over here, right, this is the difference to what you just saw in entropy, right? So the edges are not as smooth. They're a bit more straight that you see over here, right? But the essential center over here is still where the highest or where the most probable places are that you're going to be selecting these samples. So that brings me to the last one, which is margin. All right. So you notice that all of these are somewhat similar, and this one also once again is based on these softmax probabilities. But the difference is that we're going to be taking the difference between the highest and the second highest output probability, right? And the smaller this difference is, right? So if we had a high, that was the example that we just had just now. If we have a frog and a toad, and they're very, very similar to each other, right? So if the frog and the toad look very similar, right? The probability distance, or you're probably going to be predicting with, I don't know, 0.8% frog, and then then you're going to be predicting with 0.1 toad or whatever, right? So it's going to be very close to each other. And the essential difference between both of these probability scores is what you're going to be using for margin, which is the smallest margin in between these, which gives you this particular map that you see here on the left. You're going to be selecting ones that are directly on the decision boundary that you see over here. So those are three different definitions that we have for difficulty-based active learning on, yes.
Well, once you the model, like what the difficult samples are, how the effect, like because it seems that you're basically teaching the model as something that doesn't apply like that.
You're actually cutting on one of the most or at a very interesting piece, which is still an open research problem. And you're very much correct. If this would work really, really, really well, and actually this is part of my research and part of what I'm really looking at. If you get very, very difficult samples that actually results not necessarily in a really, really good generalization, so you don't really get a high curve, but it goes into a very, very low curve. And the reason is exactly like you said, right? So if I take samples that look a lot like if you take just samples that were of frogs that look almost like toads, right? And that are directly on the decision boundary, it's very difficult for the model to generalize to these, which essentially results in a worse performance. But as I will show later on in these open research problems, right? That the fact that we're training the model on very limited data is actually going to help us in randomizing this just enough, right? So that that we're able to achieve a higher performance. Okay, that brings me to the next piece, which is diversity-based approaches. So we just talked about difficulty, right? So the ones that are most difficult to generalize to. Now we can think about a different way of how we can define informativeness. Namely, we can think about the ones that are most representative of the data set. So, right? So the ones that represent the structure of this data set the most. So if we think about our representation that we have up here, right? Think about something like class centroids, right? So at the center of these different classes, these are really ones that are representative for the data set. That is one other way you can essentially look at informativeness, right? And these are different. I kind of listed two different examples. I'll be talking about what the core set is in a moment, but the idea is all kind of centered around this topic of going for the ones that represent the structure of the data set. Now, I'll be showing you two different types. First one is going to be core set. The second one is discriminative active learning. So let's dive directly into it and talk about what core set actually is. So the way you can think about what the core set of a particular data set is, it represents the samples that cover the entire data set, right? So if you think about this humongous data set that you see over here with these reds and blue points, this blue point, right, those represents the core set. That means they kind of cover the entire data set with this distance delta S, right? That's really what this thing is. Now, if you look at the acquisition function, you notice something interesting, right? And that's that we put in this loss term, right? So it means that we're looking for the samples that's these blue samples together that best approximate the loss of the entire unlabeled pool, right? So that's what this one is. This here is the loss of the entire unlabeled pool. And this here is the loss of our acquisition batch. So the samples we want to label and add to the training set. We want the loss of this acquisition batch to be the closest to the loss of the entire unlabeled pool. Problem is, in order to evaluate the loss, you need labels, which we by definition don't have in the unlabeled pool. So that's kind of where there are a bunch of different algorithms that are really approximate this core set. And the most famous one here is this greedy K-centers algorithm. It's not really at the center of this lecture, so I have the paper at the end and the resources. If you're really interested in this, I'd recommend you read it. But the idea is that you initialize a small labeled subset and you calculate a utility function, which is typically based on the distance in the representation, right? And you add the sample with the highest utility to this core set, right? And you keep on doing that until you converge.
So just verify the core set like data, so that delta is just saying that the data inside there just spans the entire like class.
Not necessarily, you don't know what classes they are, right? But they span the data set, right? With a distance of delta S, right? That's kind of the idea of it. So with the delta S, there are also some theoretical guarantees that go into this, right? So if you can span it with delta S, that's kind of one of the guarantees you want to give with this core set. That's how this thing is defined. Yes.
Do you assume all data belong to one of your there's no anomaly
Depends how you define in distribution and out of distribution. So I can give you a setting where there's out of distribution in it, and I can give you a setting where there's no out of distribution in it, right? So that depends on the problem you're looking at.
Regarding the classification tag with like output, really this size should be equal to the number of classes.
Oh, that's what you mean. So you're essentially saying you know the amount of classes or you don't know the amount of classes. Once again, you could look for there are a ton of different settings I could think of, right? So one setting is where you know all of the classes, right? So where you know which classes are in your unlabeled pool. The other one is that you don't, but you know which classes you're interested in. And the next one is where you don't even know the classes that you're interested in, and you have a humongous amount of unlabeled pool. So think about all of these three different things kind of go for different solutions, right? And that's I guess application dependent, depending on what you're interested in.
Very important step is that you really know that.
Yeah, in this lecture, we assume we know all of the classes beforehand. That's the simplest case, and that's the one I'm going to be looking at in this lecture. But in general, it's application dependent. would be my answer to this.
Hard case just principally. But if you don't know what the consequence, I don't know what that's about.
Well, you have some kind of prior domain knowledge.
I think we need to really put a framework.
Yeah. Yeah.
So we have application cloud. A lot of them people spend half the money. These are different stuff. These are two things. And that's what the whole point is. Which cloud is this kind of one? The time. That's what it is. So that's very important. This one, you can think of this as clustering within the whole acquisition function. You can think of what Brian is showing in the slide. It's clustering different things. Right? The key is what he has up there. What is the most representative task? So you can think of this as clustering within the whole, not really the essential piece.
If you're super interested in it, send me a message or something. We can talk about all of these different settings as well. Also very interesting research problems. There are also some, not a lot of papers in that area, but there are one or two that I can direct you to. So that kind of gave us this core set approach, right? And now I want to talk about discriminative active learning, which is a lot more intuitive, or it's not more intuitive, I would say, than this core set approach, but it's simpler to like really grasp in terms of what the acquisition function actually looks like. So the idea of discriminative active learning, once again, the same idea is to really find the most representative samples in your unlabeled data, right? So over here, the idea is it consists of two separate steps, right? The idea is we take another network, right? Some kind of different network over here, which is not related to our current model, right? And we train it to classify this whole entire amount of data pool into unlabeled and labeled, right? So essentially this thing we train with a binary classification label, 1 being labeled and 0 being unlabeled on all of these different data sets. And then we select the points with the highest unlabeled probability, right? So that's a different way that you can essentially go about this. Now, if you look at the acquisition function, what this essentially means, right? So if you have the A again, and you want to maximize it with a certain acquisition batch, so you want to find the samples which have the highest amount of informativeness, you essentially take the ones with the lowest probability or that are least confident in being unlabeled, right? That's what really this discriminative active learning paradigm is essentially about. And once again, this results in the similar effect of you trying to choose these representative data types. So that brings me to the next part, which is, fusion-based active learning. So is difficulty-based active learning and diversity-based active learning, are both of these clear? Is it clear from the intuition what we want to select? Is that clear? You don't look satisfied. The one he suggested, select one from each class, is diversity based. Exactly. So if you were to select each class one, get a complete view of the classes, you could see that to a certain extent as diversity based approach, if you have a balanced data set. But now I'm getting too detailed. Okay, so diversity, difficulty based, clear? Cool beans. Okay, so we just talked about what difficulty and diversity based is, and now we get kind of to the place where we move to state of the art active learning algorithms. So these are actually very hot topics, and these are usually papers that are these are the ones where typically get the highest performance. One of Google's biggest papers in active learning right now uses this fusion-based approach. And while I'll not be talking about like the specific algorithms here, because they're actually very different and they depend on like the specific setup. I'll be talking about the intuition. And in the resources, I listed a couple of papers which are very new, or some of them which are compared to a lot. If you're interested in specific other papers or whatever, I have a big list on these. So if you're really interested and want to dive into the subject, send me a note. So the idea behind this is to kind of get the best of both worlds from difficulty and diversity, right? So one of them gives us these centroids that we have at the far point, right? And the other one gives us these outliers, right? Which are far away or close to the decision boundary. Is there a way we can somehow marry both of these and select some of these and some of these to essentially optimize the performance? And that's what really fusion-based approaches are about. And just to kind of like outline of how a typical fusion-based algorithm looks like, right? You could you essentially rank, or some of them rank samples in terms of difficulty, and then integrate some kind of sampling algorithm to start to inject some randomness in this difficulty-based sampling. So your example that you mentioned earlier on, right, where you said that difficulty will result in worse performance, if you select and add a bit of randomization to it, you can already imagine that if you bias towards the difficulty ones, but you add some randomization to it, you could achieve a lot higher, because it does not only mean that you're going for the ones that are closest to the decision boundary, but you're allowing some relaxation in the sense, right? That's essentially what these fusion-based algorithms try to do. And they all do it in a very different way. And they all kind of do, they estimate difficulty and diversity in two different ways. And they typically mix both of them in one. So any questions about this one here before we move into open research problems? Okay, cool. Then let's kind of talk about open research problems. And this is, as you can imagine, this is really where we see the limits of what we can actually do. And I think this is probably one of the coolest parts of this lecture, right? So what I want to talk about are two different areas. The first one I want to talk about is active learning under limited data. So as you can already imagine, right, the training set we're training our model on to select these data points already has only limited data available. So what actually happens when we train a model only on a smaller amount of data? How does that affect these representations? And how can we essentially get around from this, and kind of, or what are different approaches we can look at that essentially mitigate this, right? Or how can we essentially differentiate these things? And the second one, which may not be directly clear, that I'll be talking about today, is performance regression. And when you take an active learning algorithm and you move it into the industry, if you move it into the real world, all of these safety critical things all of a sudden are super important. So think about the self-driving car example. I have a small data set, right? And now I increase the data set by having my model select these samples. If by increasing this data set, I am able to detect all cars really, really well, but I slightly reduce the performance I have on pedestrians, you can already imagine that this model is very, very difficult to deploy. I'll go more into detail on this later on, and I'll give you a very explicit example of this, right, in the self-driving car space. But just to give you kind of a taste, that is really what I want to be talking about today in the second part of this. So that being said, let's kind of move to how these algorithms actually work. So we talked about these three different buckets. We talked about the difficulty-based approach. We talked about the diversity-based approach. And we talked about mixing the two with the fusion-based approach, right? So all of these kind of result in very, very different samples you select, as I've already seen, as you see over here. These ones select the outliers. These ones select the class centroids. These kind of do a mixture of both. So you could imagine that the results of these active learning algorithms are going to be very, very different, because the definition of informativeness is very different. But there's one key assumption here that we made, which is not given in practice. And that's that this representation is going to be very informative for this acquisition function, right? So that this, you can essentially imagine that this thing is very much spread out. But that is not necessarily the case in practice. And things can actually look like this, right? So this is something we call feature collapse. That means if we map two different samples to the same feature, which are completely different, and we're not able to distinguish them, right? And this is what typically happens a lot under limited data. That means instead of that nice spread out distribution that you just saw in the feature space, all of a sudden this model is not capable of distinguishing these two things, right? And essentially maps them, collapses the features to very, very similar points, right? That's what you can see over here. And as a result, right, if you'd like plug it into the active learning algorithm, you of course get a lot more randomization, which is what we discussed earlier with the randomization automatically happening, right? That's really this aspect that's happening. If you map data samples to the same point, right? It doesn't really matter if I go for difficulty-based approaches or diversity-based approaches, right? Because they're all mapped to the same point. I can't distinguish, if they're all in the same point, I can't distinguish the ones closer to the decision boundary from ones that are far away, right? That's the big problem here. Is this problem very clear? Okay, cool. Nice. So I kind of want to, while we haven't really, I wouldn't say there's like a single solution to this problem, right? We haven't found a single solution that really mitigates this. But there are different approaches that you can essentially take to avoid this. And one of these is essentially looking at not the model representation directly in. And now I'll be taking a short detour to kind of defining how we can look at these model representations, not directly, but how we can look at it in terms of shifts, right? And that will give us a different measure of informativeness that we can use over here. So that's kind of what Hassan mentioned earlier on, where I'll be diverging a bit towards forgetting events and switch events, the stuff that the stuff that he talked about earlier on, and that'll give us a very nice definition of informativeness. So let's kind of take a small detour and define what informativeness means with the way a representation can shift. So let's first define what a representation shift is. So if you think about these two, if you think about the output representations, right, those FW, etc., right? What we want to measure now is not the exact position of it, but the way this position evolves and shifts during training, right? So if you have two different models, one of them is at some kind of time t, and the other one is at t-1, so that's some kind of previous time during training, right? And at t, it predicts frog, right? So if you imagine those three different classes, right, that means it's deep into the frog area, right? But earlier we predicted toad. That means the representation shifted from one cluster to the other, right? It gives us the actual difference between both of these. And that's really what we're trying to measure. That's what really a representation shift is from an intuitive sense. From a mathematical sense, it's that mapping in between these two class manifolds. So that's what we're going to be doing. We're going to be predicting frog over here, toad over here, and we're going to be looking at the accuracy difference. So one way we can look at a representation shift is how it shifted from incorrect to correct or correct to incorrect, right? In this case, a forgetting event, as the name already suggests, it means that we learned it in a previous point and forgot it in the current epoch, right? So that's exactly what you can see over here. The current epoch predicts frog. Previously, we predicted toad. This is a toad. That's what we count as the model forgetting something, right? Even though we're talking about forgetting, it actually means the representation shifted in between both of these. Is that clear? Cool. Yeah.
So just forgetting events is just when it switches between like different classes.
Not between different classes, between the correct class and any incorrect class, right? So that's basically, you can think about it intuitively. If I learned something previously and I forgot it now, that's what I call a forgetting event, right? That's what you call when you forget something. Those are the ones that are shifting, right? So in that sense, yes. We have a So if you think about the workflow we had earlier on, right? So we had the unlabeled data, right? And it went into our model here, right? And we had the training set at the bottom over here, which we denoted that was training. This sucks. Ooh, dude, nice. You come prepared. Nice. Love that. Okay. Right. So if you remember our previous diagram, which looks like this, right? And you had the training subset over here, right? Which we were training the model on, and then that went into the acquisition function over here, and we annotated it and added it to the training subset, right? So where this is happening is exactly this stage, right? So where we train the model on the labeled subset, right? So this is what's happening during training. And if we look at it during training, if we learn something at an early stage and forget it at a later stage, right? That's what we call a forgetting event. Yes. Yeah, exactly. That's why we're not going to be using forgetting events. We're going to be using switching events. Yeah. Exactly. And it has this very nice intuition of you forgetting something. Every one of us can kind of relate to us forgetting stuff, right? So that's also the premise behind this. So our forgetting events clear. Cool. So as you already mentioned, there's a really big problem about forgetting events. And that's because you need labels to quantify a forgetting event. You need to know that this sample is a toad to know that it's incorrect now and that it was previously correct, right? So problem is I can't really evaluate that on the unlabeled pool. So if I want to count forgetting events as a measure of how informative a sample is, I cannot do that on the unlabeled pool because I don't have any labels. And that's exactly where these switch events come in. Now, oh yeah, I actually forgot. This is I forgot this slide. This is the formalization of this actually. Sorry, before we talk about switch events, I quickly want to talk about the formalization of this. So if you have an accuracy at a time t, which is simply the notion that your label is equal to the predicted label, right? So the true label is equal to the predicted label, that evaluates to 1. This is a binary variable that that essentially evaluates to 1. That gives me the accuracy for that sample at a time t, which is binary. It's 1 or 0, right? And a forgetting event happens if this accuracy value essentially decreases in between 2 different epochs, right? So if it flips from 1 to 0. And if I sum up all of these over all of the epochs, right? So if you think about the sum of this over all epochs, that will give me a number for each sample, which I can essentially envision as a way of informativeness. If I would be able to measure this with forgetting events, which I can't, because we're going to be talking about switch events in a moment. But that's to the formalization.
Probability after off-max, it went from 49% down 52, which is why the class shifted.
So you don't look at it in that detail. This one here is binary. It's 1 or 0. You could come up with ways to integrate that as well. There are also some issues with that simply because neural networks are not as well calibrated. So getting a 0.5% with a badly trained network, which you do because the labeled subset is very small probability that that'll happen. But if you have further questions about that, hit me up. So yeah, that quick detour of what these things mean formally and actually give you a view of how you can essentially use these or could use these in active learning if you would have labels. So now that we know that we don't have labels, let's kind of take this notion of forgetting events away and bring it to switch events that we can use on the unlabeled data, because switch events don't require labels. So remember that forgetting events happens because we classified something correctly in the previous epoch and are now not classifying it correctly. Now, a switch event essentially is the same concept, but it doesn't look at correct, incorrect. It just looks at that the prediction switches, right? So instead of thinking correct, incorrect, it just looks at, well, class 1, now it's class 2. So the idea is that we're switching in between these. Now, if we look at this and our example here on the left again, right? The previous epoch, we could be predicting something like fly, and now we're predicting frog, right? And in this case, both of these are incorrect because it's a toad, but we would still count this as a switch event because the prediction here is not equal to each other. I'll formalize this in a moment also. So that gives us a very nice way of looking at information content, or essentially some measure of informativeness in active learning. If we just take the samples that have the most amount of representation shifts that are happening in between these different epochs, right? So the big advantage is we can use this on the unlabeled pool. So let me kind of formalize this a bit before we now move into the question part. If we define some kind of prediction, right? So this is the output probability vector of your current model, right? Given at some time at epoch t. Now, a switch event occurs if the current prediction, right, is not equal to the previous prediction, right? So if you evaluate in 2 different separate epochs during training, right? If the prediction switches, we simply count that as a 1, otherwise it's going to be a 0. Right? And if we want to summarize this across an entire active learning round, we essentially take the sum of these switch events. So imagine these ones being 1 or 0 in different epochs, right? And now we sum over the entire round, meaning over all of the epochs that we do during a round. So think over here during training, over all of the epochs, we sum up all of the switch events, which give us this score at the end for each sample, a number. Yes. So the answer is there's no really clear way to give you a definite, and there's no definite answer to this. It's an open research problem, yes. But it depends when the switch events are actually happening, if you want a more detailed answer. If they're happening very far at the end, then yes, right? Because that means that our network has already trained very well, right? It already has a certain idea of the data set. And that means that if it's switching in between 2 classes, right, those are very ambiguous samples. But if it happens at the beginning, not necessarily. So there's like there's a progression that you can see when these switch events are actually happening. Yeah, that would be my short answer to this. Once again, if you're interested, this is I work in this area, so shoot me some questions. So yeah, now we kind of let me kind of really illustrate why this notion of representation shifts or these switch events essentially have a potential to well, kind of give us a different view of these samples, even though we collapse them to the same point. So if you remember in the earlier problem that we had a very well-defined input feature space, right, where we had a very nice distribution that you would plug into the acquisition function, which, depending on the definition that you use, right, would give you very, very different answers. Now, in reality, I showed you that all of these collapse to single points, if you remember a few slides back. Now, imagine you have this model here that collapses these different points, right? And this is really the classical, the thing that I just showed you, right? So all of these different samples that you see here on the left are all collapsed because we only have a limited amount of data available. Now, if you look at 2 different epochs, both are going to be collapsed. Both of them are trained on the same training data. Both of them are essentially just looking at the same unlabeled pool. They're all collapsed in these areas. Now, if I were to look at the final one, so let's say this one here is the final model that we look at and that we use for selection, you notice that no matter which definition, difficulty, diversity, or fusion we would use, would not be able to distinguish these samples very well. We would not be able to make a very accurate prediction. But now if we incorporate this prediction switch notion, right, we're not looking at a single model anymore, but we're all of a sudden looking at the way or the dynamic at which these models switch in between these different places. So think about not looking one of these anymore. Now you're looking at the dynamic between two, and you're looking at how they move, right? So you don't really care that they're mapped to the same point. You care that they move. You care that they move during training. And that's really what this particular algorithm is about, where you essentially sum up these representations. So now your question would probably, how much better does this perform? And it performs a little better, as you can see over here. So this blue curve over here is what you would define as the switch events. And this is a very popular example of the CIFAR-10 test set. And these are the size of the training set as you increase it over time. And these are different algorithms that you're testing against. So core set is the diversity-based one. Entropy and these components are those two difficulty-based approaches that I presented earlier on. Active learning by learning, this orange one, is a fusion-based approach, okay? And this one over here is essentially this representation shift one. So even though this particular example here doesn't look like much, the reason why this is also happening is because this is a very, very tiny data set. This is CIFAR-10, right? CIFAR-10 has 50,000 examples. Active learning gets interesting when we're looking at millions, right? And that's where the differences get more profound. Now, in research, we don't have the resources to essentially evaluate on millions and millions of samples. That's more of a Google or Facebook thing. That's why you have to take all of these things with a bit of a grain of salt. But the most important thing is it's promising, right? Especially this beginning piece. It means that with a very small training set where you have a lot of collapsing happening, we're outperforming using these representation shifts and a bunch of different, we're really outperforming at the beginning stages where the training set is especially small. And you also notice we did a lot of simplifications in the representation shifts, right? We're only looking at binary things, for instance, something you mentioned earlier on, right? What happens if you incorporate a lot more of this? How much more information can I add to these representation shifts? How much more can I extract from them that will essentially allow me to increase these? And that's where research is. That's where it's at, if that makes sense. Okay, that concludes the first part of it. Are there any questions? Yes. Yeah, so you evaluate it on the unlabeled pool during training, and then you can pick the ones with the most amount of switch events and then add them to the test set. Not test sets, to the train to send them to the labeling company. The labeling company labels those, and then you can add them to the training set. Yeah, that's exactly what's happening. So yeah, are there any other question about this area? You see that it's a very, very difficult problem to solve, and that is still very, very much room for improvement. That's what I just showed you, right? And that's what I think is so exciting about it, because it means something we can work on, and that really makes a difference, as you can imagine. Not sending tens of millions of samples to a labeling company that will cost you billions of dollars. Let's just send them 100. That will give us the same amount of performance boost, right? So there's a lot of money behind this, and there's a lot of companies looking at this like crazy, and it's really at the center of, or it's at a very interesting part where both academia and industry are both converging and really want to find a solution to this. So yeah, that kind of concludes this first part of limited data. Now let's talk about performance regression. And now if we switch gears, right? I introduced this as in what happens if you add more training data and the performance decreases, right? What happens if the performance decreases? Now, why is this interesting? And I really want to talk about with a particular toy example that you see over here. Imagine you want to do autonomous driving, right? You put a car, in this case, put a camera on a car. In this case, it's a Mercedes. This is the Cityscapes data set, if you're ever familiar with it. And you drive around for hours and hours, and you essentially want to say which video subset of this one do you want to send for labeling. So imagine you already have a labeled subset, right? And you just trained your model on it, and now you want to evaluate it in real time. Let's say the first or at a certain active learning round, meaning with a certain training set size, you're going to make the following prediction, right? You're going to predict the bicyclist over here. You're going to predict these 3 different cars, right? And you're going to have a false positive sign over here, right? So this particular sign, we're saying it's a pedestrian, or the algorithm is saying it's a pedestrian, even though it's not. And well, at the same time, you also have a pedestrian over here that we're classifying correctly, right? That gives us a total accuracy of around like 87%. So if we take, or if we increase the training sets and just look at the numbers, right? So if we if we select our samples, label them, add them to the training set, and retrain our model on the bigger training set, right? That increases the overall accuracy. So just looking at the numbers, if you look at the curve that I just showed you, it would actually be higher. It would actually go up, right? So we're looking at 89%. And now let's actually look at the predictions of what they look like. So you notice we're all of a sudden able to predict a car that's further away, which is actually a very, very important problem, right? You're able to predict cars that are only half in the picture, also very important, right? And you're able to get rid of false positives. If you're ever working in a company, getting rid of false positives is going to be one of the most important pieces you're going to be working on. But most crucially, you miss this pedestrian. And just looking at that, right? Really big problem. Because what if that pedestrian runs into the street? Well, it's massive lawsuit. You're never going to be able to deploy this technology ever again, right? So you see that this pedestrian here, even though the accuracy goes up, this pedestrian is actually really important to predict, and this pedestrian is is essential for you to be able to deploy your active learning algorithm. And that's what we really define here as what we call performance regression. That means over a model update, even though an update happens, right, the performance decreases, namely over very specific samples. And I'm going to be taking the next couple of slides to really formalize this. And once again, to remind you why it's important is, first of all, stopping criteria. In this case, even though this model here may not be as accurate, right, it's still able to more reliably detect the pedestrians. Maybe you want to stop over here, right? The next one is, well, do we want to deploy our active learning algorithm at all, right? And of course, the actual quality of your acquisition function also comes into play here. So let's start formalizing what regression actually is. And in order to formalize it, let's look at a very simplified setting over here on this 2-class problem. So you have these 2 separate classes. One of them is going to be green, the other one's going to be blue, okay? In round n-1, so on our smaller training set, right? That gives us this line you see over here, this decision boundary. And if you increase the training set, it gives us this decision boundary. So just looking at this, you can do 4 different classifications. Both models can be correct. Those are these samples over here. Second one, both models can be incorrect, right? So these are these samples over here. Even though we moved from here to here, these green ones are still misclassified as blue, and these blue ones are still misclassified as green. Now, the ones that we're really interested in are these 2 other ones, namely both negative and positive flips. You can have positive flips, right? Those are the ones you previously incorrectly classified and are now classifying correctly. Those are these 3 samples up here. Those are usually a lot higher because you're actually increasing the training set, right? And then at the bottom over here, you have the negative flips. And these are the ones we're really interested in and that describe regression, right? Oh, wait, which one was the negative? Yep, no, it's the top ones. Sorry, oops. My bad. These bottom ones over here are the positive flips, and these ones up here are really the negative flips that we're really interested in. How can we essentially now formalize this into a metric, right? So I just discussed what negative flips are. I hope that's clear. Are negative flips clear? Okay, now let's actually put this in the metric. And that's the ratio of total negative flips happening in your entire data set. So if n is the size of your data set, right? And then you count the samples that just flipped from positive to negative. So all of your negative flips divided by the total amount of samples, that gives something we call the negative flip rate, which essentially amounts to the ratio of negative flips happening. Low negative flip rate, great, means very, very little regression happening. High negative flip rate, really bad, right? So now let's look at this more in this graph, right? So if we have a model at round n-1, smaller training set, and round n, right? We missed this particular pedestrian. This one we count as a negative flip, and the ratio of all of these gives us the negative flip rate. So yeah, this really just sums it up. The old model in our previous toy example is the previous round, and the new model is the current round. Now, I kind of want to show you something over here, which is actually a really, really exciting result. If you think about the negative flip rate, right, and you increase the training set, that means your model has more data available. It's able to extract more intricacies from these classes. It's able to have a more holistic view of what the data looks like. You would expect the negative flip rate to reduce in that sense, right? You would expect that our model is better informed. That means it will consistently map samples correctly, right? And that they won't be flipping as much. In other words, as the accuracy goes up, right? So this is this green curve, the ones that I showed you earlier on, you'd expect the negative flip rate to drop over time, right? Over the size of the training set. Now, what I'm showing you here is the negative flip rate on CIFAR 10, and I'm showing you the negative flip rate on CIFAR 100. Two different data sets. One is more difficult than the other. But most importantly, you see that the negative flip rate reduces over time on CIFAR 10, but on CIFAR 100, it increases over time. Meaning, and I didn't plot the accuracy curves here, but if you look at the accuracy curves, they'll actually follow exactly this green trend that you see over here. That means essentially, even though our model is generalizing better and is essentially getting a higher test set performance, we're actually increasing the amount of negative flips that actually happen throughout this. And that's really interesting. That means, where are these negative flips coming from? It's obviously not directly tied to how well our model is performing on the test set, which is a problem in practice, because that means we definitely need to look at this, right? We definitely need to understand how many samples are flipping constantly, right? And the second thing it actually means is, well, can we actually, what constitutes to a negative flip rate? Is it just class complexity? Is it just the sheer unbalance of the data set? All of these different questions are very much still in the air. Yeah, it's a very exciting topic. So that brings me to the end of this lecture, and I'm exactly on 75 minutes. Nailed it. Are there any questions about regression? Are there any questions about anything we talked about today? Cool. Sounds good. Let me know if you have any. I super love this topic. So like I said, love talking about it. If you guys are interested in it, I love explaining this kind of stuff. Super exciting, super fun. And yeah,